Photonic nanostructures map out the dispersion relations of the confined electromagnetic modes in a photonic crystal and are associated with enhanced light-matter interactions such as magneto-optical effects. Our method enables the mapping out of magneto-optical effects in the reciprocal space of the photonic crystal so that we can directly study how magnetization modifies the photonic response.
Magneto-optical crystals are interesting for their non-reciprocal optical properties. While we will demonstrate this technique with a simple plasmonic grating, it's applicable to many other types of photonic crystals. One particular challenge of this technique is that the magneto-optical effects are typically very weak, so you have to take extra care to make sure that any noise is minimized.
Begin by building the setup on an optical table with sufficient vibration isolation. The optics of the beam emerging from the sample should be set up as indicated, with the infinity-corrected objective lens directing wave fronts emerging from each point of the sample into collinear beams. Place a collector lens with an f of 200 mm, 330 mm from the objective to refocus the beams to form an image at the image plane. Insert a flip mirror after the image plane to enable real space imaging of the sample. And insert an L1 lens with an f of 125 mm so that the image plane is in focus. Place an L2 lens with an f of 250 mm at a 135 mm distance from